Okay, so now let's move on to an example of an application of the harmonic oscillator model to the infrared spectrum of HCl. So the infrared spectrum of HCl in the gas phase is dominated by this vibrational transition that we can describe using the harmonic oscillator or particle on a spring type model. And so our molecule here is HCl, vapor, and the masses in this molecule are mass of hydrogen is 1 atomic mass unit, mass of chlorine 35 atomic mass units, and here we're using atomic mass units. You can use either mass of a proton, which is 1.673 times 10 to the minus 27 kilograms, or you can use Daltons, which varies a little bit from that due to the way they're calculated. They're close, but the standards are a little different, and it has to do with differences in the energy of the nucleus. The arrangement of protons and neutrons in the nucleus for different atoms has different relativistic energy, and thus a relativistic mass, and it varies by some fraction of a percent, maybe a few tenths of a percent, something like that. But we're going to just use integer masses where we, for a given isotope, say the chlorine 35, that's just the number of protons plus the number of neutrons. The actual mass in terms of mass of protons or in terms of Daltons or kilograms is going to be a little bit different than that, but we're not going to worry about that too much. That's important for very, very high resolution type measurements that we will probably not be doing. So let's see. Some other constants. We have, of course, Planck's constant, h, that will show up, and there may be some other constants such as speed of light, c, that's going to show up. The other sort of parameter, the sort of setup of the problem is that we're assuming that we somehow know this spring constant K, that K is 480 newtons per meter, and maybe this comes from some kind of calculation, or it comes from some estimate based on other similar molecules, or it comes from ab initio calculations or some other method. And we're not going to worry about how we know that, but we know it. And then the question is, given all this, can we calculate what is the infrared transition for this molecule? So for HCl at room temperature, most of the molecules are in the ground vibrational state, the V equals 0 state. That's the lowest energy state. And that the infrared transition corresponding to absorption of an infrared photon is the V equals 0 to V equals 1 transition. There are other transitions as well. This is the more intense one, and it's well in the infrared range. And so we're interested in what's the energy difference between the V equals 1 and V equals 0 state. And also that energy difference is going to be equal to h nu for a photon, right? This is the Planck-Einstein. equation. And so we're interested in what's the frequency of that photon. And once we know what the frequency of that photon is, we so we want to calculate the frequency, and then we want to convert from frequency to wavelength. Maybe in microns or nanometers. Infrared, it's usually in the micron range. And of course frequency, that is in hertz. And there's another unit that is used a lot in infrared, is used primarily. It's the one that's the sort of typical unit for infrared spectrum is something called wave numbers. So you pronounce it wave numbers, but it's actually written reciprocal centimeters. And so we'll want to turn this frequency into this into nu tilde, which is the frequency in wave numbers. And again, this is a unit that is so frequency and energy are proportional to one another when we're talking about photons, and so we can think of frequency as a type of energy unit, and similarly wave numbers we can think of as a type of energy unit. We should treat it as an energy unit, and there's a reciprocal relationship between wavelength and frequency and wavelength and energy. Okay, and let's see, so what else did I want to say about, oh yeah, wave numbers. Yeah, typical infrared spectrometer, like an FTIR, usually goes from 500 wave numbers to a few, I forget exactly, it's maybe 3,000 wave numbers, or 4,000, I think maybe it's 4,000 wave numbers. And I know the other end is around 500 wave numbers. And below that, you're kind of in the the very far IR, or the kind of microwave end of the spectrum. And so we're going to want to know that frequency and wave numbers. What else do I want to say about wave numbers? Oh yeah, the conversion. So wave number it's a special spectroscopic unit, and based on the unit is kind of defined more based on the fact that infrared spectrometers typically had gratings in them, and the gratings had a certain spacing associated with them, and so you could, based on the angle of the grating and the ruling spacing of the grating, you could wave number was a convenient unit, and you know, the distance, also the focal distance of the spectrometer. So all of those things went into an equation. You end up with a convenient unit that could be sort of defined mechanically, was this wave number unit. Whereas you couldn't directly measure, say, the frequency of the light, but you could sort of directly measure the wave number. And we can think of wave number is it's a way of, you can imagine sort of taking your photon and freezing it, stopping it at one moment in time, and then counting the number of waves per centimeter. Waves or wavelengths. And so a higher frequency light is going to have more waves per centimeter. And let's see what else to say about wave numbers. Oh yeah, the relationship between wave number and frequency in hertz. If you have frequency in hertz and you divide by 100 times c, where c is the speed of light in meters per second, the factor of 100 converts it to centimeters. So we've got centimeters in the denominator. And again, and it's c, so we're talking about the speed, we're talking about light, so that's the right speed to use when converting between sort of a wavelength or an inverse wavelength and a frequency. So that's the conversion. Okay, so now let's move on. So how do we solve this problem? First, we know that our frequency, our classical and our sort of quantum mechanical harmonic oscillator frequency is 1 over 2 pi square root of k over mu. So we have k already, and that square root is supposed to extend over both of these things. Now we have k already, we don't have mu. Mu is the reduced mass, and for a diatomic, we use m1, m2 over m1 plus m2. And then if these are in sort of integer atomic mass units, we'd multiply by the mass of a proton. And so by sticking to integers, this simplifies the problem a little bit. We get mu is going to be 1 times 35 over 1 plus 35 equals 35, 36 times the mass of a proton, or times the Dalton, which is 1.662. And we notice that this is a number, 35, that's a little bit less than 1. And this is a common feature when you're dealing with two nuclei that have very different masses. Often typically, the reduced mass is going to be just a little bit less than the mass of the lighter atom. And so the lighter atom here is the hydrogen, the proton, and it has a mass of 1 times the mass of a proton. And so we end up with 3536, which is a number that's a little bit less than 1, right? It's a few percent less than 1. And so we should end up with a number that's close to so we end up with 1.626 times 10 to the minus 27 kilograms. So it's very important at this point, our mass should be in SI units, in the base SI unit of kilogram. in order for this to work, because then when we plug in to get our frequency, so we're going to calculate our frequency is going to be 1 over 2 pi square root of k over mu, and so that would be the square root of 480 divided by 1.626 times 10 to the minus 27, and that's going to give us 8.65 times 10 to the 13 hertz. Okay, and so let's pause, and so this gives us an order of magnitude that we should carry with us going forward. Roughly, vibrational frequencies are on the order of, say within an order of magnitude or so of 10 to the 13 hertz. So that's a very high frequency. Audible frequency is 20 hertz to 20 kilohertz. This is billions of times more higher frequency than that. Okay, so it's not something you could hear, right? It's something you can see with your eye. If you can see the photon anyway that has this frequency. Okay, so then that's our frequency. Now we can convert to an energy. So that's our sort of base frequency. Our delta E is going to be E for V equals 1 minus E for V equals 0, and that's going to be equal to 3 halves h nu minus 1/2 h nu, which ends up being h nu. And interestingly, the frequency of the photon is equal to the frequency associated with the energy difference between the transitions. And so then the energy of our photon is going to be h nu. And so if we multiply that out, we get 5.73 times 10 to the minus 20 joules. Of course, that's per photon. That's not per mole of photons. So we expect a very small number when it's on a per photon basis. Per mole of photons, it's going to be, maybe several joules or kilojoules or something like that when we plug in Avogadro's number. The frequency in wave numbers take nu divided by 100c, we get 2880 wave numbers. And again, I said that the infrared spectrum is ranges from about 500 wave numbers to several thousand wave numbers. I think I said previously 3 or 4. I think it's more like 4 or 5,000 wave numbers. And so this is what we expect. So if you get an answer for wave numbers that's 0.1 wave numbers, or that's 10 to the 19 or 10 to the 20th wave numbers, that's not in the range of what you would see in a spectrometer. So probably something's wrong with your math somewhere. Similarly, with a frequency, we expect this kind of very high frequency. If you get a vibrational frequency that's 10 to the minus 13, then you probably got things a little mixed up or entered something into your calculator wrong. And because, of course, we expect that the vibrational frequencies, this is a really tiny spring and really tiny masses, and you expect the frequencies, the corresponding frequencies, to be rather high. You wouldn't want it to be, say, something like 10 to the minus 13 hertz. That would be the vibrational period, that's like the age of the universe or something. So yeah, that doesn't make sense based on our knowledge of the world around us. Okay, so 2880 wave numbers is what I get, and again, that's where we'd expect the peak to show up in an infrared spectrometer. And in terms of wavelength, lambda is c over frequency, and we get uh, 3.47 times 10 to the minus 6 meters, so 3.47 microns. And that's, again, in the infrared spectrum. We know the visible spectrum extends from about 400 to 700 nanometers. So the near IR is maybe 750 to nanometers to say 1.3 or so microns. And so this is 3.47 microns. So it's not even in the near IR. It's the sort of middle of the IR. And that's the infrared spectrum. Now, there's other ways of, there are some similar related problems. You could be given the photon represented in any one of these ways in terms of wave numbers, the reciprocal centimeters, or in terms of the micron wavelength, or in terms of the frequency, or in terms of the energy of the photon. And then you could be asked, what's the corresponding spring constant? Or if this spring constant is known, the energy is known, but the reduced mass isn't known, maybe you could calculate that. So it's basically a set of relationships here that can be rearranged different ways to go from what you do know to what you want to find out. Now there's a related issue, which is the isotope effect, which I alluded to when we started this lecture. And I should not say the isotope effect. This is the isotope effect for vibration. The isotope effect for rotation is different. I mean, there's some somewhat similar features, but the actual functional relationship that we get is a little different. And so you can use actually an infrared spectrometer to give you some information about the presence of various isotopes. And the presence of various peaks corresponding to different isotopes can give you clues about the nature of the molecule or of the vibration. So it's useful information in some cases. And in any case, it's something that we expect to see. And then so this question is, what happens when we go from, there are a couple of different isotope effects we could look at here for vibration. We could look at HCl going to DCl, where we replaced hydrogen with deuterium. And deuterium is just hydrogen with an extra, with a neutron. And so it has a mass of 2 AMU. And we could also look at the two different primary isotopes of chlorine, chlorine 35, chlorine 37. We're going to look at the deuterium case, and we can leave maybe the chlorine case, the different chlorine isotopes for a homework. So what do we know about isotopes? Isotopes have the same same basic nuclear charge, just a different mass. And the other thing that we know is that they're chemically virtually identical. In other words, if you have heavy water, it has a boiling point very close to the boiling point of regular water. So, you know, D2O very close to H2O in terms of its boiling point. You know, the bond strengths are going to be similar. So therefore, what do we expect the spring constants to be like? So there, based on this reasoning, we would expect that the spring constant in the vibration of DCl is going to be the same as it is for HCl, right? You know, that's just based on what we know about isotopes. Okay. However, the mass we expect to be different. So essentially, we're looking at what is the effect of changing the mass on the frequency, and we expect no change in the spring constant. Let's see. So here we so then our question is, if we know that for HCl our vibrational frequency in terms of wave numbers is 2880. What is the vibrational frequency for DCl? Okay, here's where it's good to employ. So we could go all the way back to the beginning, start this problem the same way, just use a different mass and get a result, and hopefully we'll get something that works out right. However, we can skip a lot of algebra steps, skip a lot of entering numbers into a calculator, and be more likely to get the right result if we properly employ proportional reasoning. Okay, we know that, let's see, so we know that frequency is 1 over 2 pi square root of k over mu, but k doesn't change in this system, 2 pi doesn't change in this system. So really what we're interested in terms of our proportional reasoning is that our frequency is proportional to, I'm using this proportional to symbol, looks kind of like an alpha. It's proportional to 1 over the square root of mu. Therefore, if we know the frequency for one molecule and we want to find the frequency for a different molecule, and they only differ in terms of their mass, then say if we have molecule A and molecule B, nu A over nu B is going to be equal to square root of nu B over nu A. Right? This follows directly from our previous proportionality. So therefore, if we know some frequency of one isotope and we want to find out what the frequency of the other isotope is, so we want to know isotope B and we know frequency of A, it's going to be the square root of mu B. Oops. Got a little ahead of myself. Let's see. So we move mu B up. So we would take the reciprocal of all this, move the nu A over to the right hand side, and that's going to give us nu B is going to be equal to the square root of mu A over mu B. And again, all of that is under the, both of those mu's are under the square root. Okay, so this is a much simpler problem, right? We calculate the two reduced masses, calculate their ratio, and you notice their ratio, if we stick with the sort of integer atomic mass units, that's going to be some simple ratio of two integers, like 35, 36, or something like that. And or it's going to be, sorry, a ratio of two integers. But anyway, so there's going to be, maybe 4 integers in there tops. So it's not, and they're going to be typically, relatively small integers, less than 100 or so. So, so this is going to give us something that's less numbers to enter in your calculator. And in the case of HCl versus DCl, it's even simpler than that. Oh, and the other thing is, let's look at this carefully. So the other thing is that we expect for heavier isotopes, the frequency is going to be less, right? If mu B is heavier than so if molecule B is heavier than molecule A, and molecule B is in the denominator here, so that's gonna give us a lower frequency, and that makes sense. The heavier strings on a guitar or something are going to be lower frequency. So we know that larger mass, typically with springy things, is going to indicate lower frequency. If you have a large mass on a pendulum or on some kind of spring mechanism in a clock, it's going to oscillate more slowly. But it's not a linear proportionality. It's proportional to 1 over square root of the mass in this case. Okay. So then we can so mu HCl, remember, is 35, 36 times the mass of a proton, and so our mu DCl, and that's almost, right, that's very close to the mass of a proton. For mu DCl, we're going to have 2 times 35 over 2 plus 35, right? Because deuterium has a mass of 2, and so that's going to be 70 37ths, which is roughly 2 times the mass of a proton. So in other words, And again, as I said previously, our reduced mass, if we have two very dissimilar masses, say proton and chlorine, where proton's much lighter than chlorine, the reduced mass is very close to the mass. It's a little bit less than, but close to the mass of the lighter of the two elements. And so, so we expect for DCl, it's going to be close to 2 times the mass of a proton. So therefore, we expect then that the frequency for DCl is going to be equal to the frequency of HCl roughly divided by the square root of 2. And that was 2880, and so this is going to give us 2040 wave numbers, and that's a lower frequency. Again, that's what we expect. If you got something like 50 times the frequency, you would know maybe you entered something into your calculator wrong. It's time to do some check some work. And also, it's a great sort of true-false question. All else equal, in an isotope effect, do you expect a heavier isotope to have a lower frequency or a higher frequency? Perfectly valid question. If you don't know the answer to that, then it can be argued that you don't know the concept. Okay, so that is a little bit about the isotope effect. Now I'm going to finish up by talking a little bit about recap a few of the key concepts on this subject, and I'm also going to try to put this in context a little bit of in terms of what does the potential energy curve look like for a molecule such as HCl, and how does that relate to the harmonic oscillator model. Okay, so we learned a little bit about the harmonic oscillator. We're using it for, we can use it to examine vibrational spectroscopy, predict the positions of peaks in the infrared spectrum in wave numbers or in frequency. And one thing that's important is it's usually the V equals 0 to V equals 1 transition that's important for vibrational spectroscopy. We haven't really talked about it, but it turns out that the harmonic oscillator is useful for predicting the heat capacity of solids. That's a starting point for phonon theory. And I mentioned that at the beginning when we first started talking about the harmonic oscillator, but I just thought I'd reiterate that. And there's this question of does the potential energy curve look like, let's see, does a real potential energy curve look anything like a harmonic oscillator? And does it look at all parabolic? And we'll get into that in just a minute. Let's see, what else did we do? We predicted the shapes of the wave functions. We talked a little bit about classical turning point and this phenomenon of tunneling, that there's some probability density outside the classically allowed region. Another thing that we won't have a chance to get into, at least for now, I may come up with some exercises related to it later, is that for triatomic or for larger molecules, of course we can't use this simple reduced mass relative coordinates approach. You have to use something called normal modes, which we probably won't have a chance to get into. But you basically take a set of coupled harmonic oscillators, and it turns out that the vibrations kind of break down to these normal modes where you can, if you know the initial masses and the initial spring constants associated with the interactions of those masses, then you can be given a frequency and a reduced mass for the normal mode. Okay. So yeah, so that was just a couple of odds and ends that I wanted to just quickly say verbally. I didn't take the time to write them down. They are in the typeset notes as well, I believe. Okay, so the let's look at the potential energy curve. Associated with a chemical bond. Such as HCl. So we know the HCl, at least in the vapor phase, there's a covalent bond. It dissociates in solution. However, there is a chemical bond in the vapor phase. And there is, so what do we know about potential energy curves going into this? So we think, or it's been posited that that it's related to or similar to the parabolic harmonic oscillator potential. And so we think that's true. So we're going to examine that. I'm going to put a question mark on that one. What we think we know a little bit better about chemical bonds is that there is a bond energy. Okay, associated with so there's an energy associated with the bond, and basically that's the difference in energy between the atoms that are associated together, bonded together, versus if you pull them apart, or if they're initially apart. So if these atoms come together and form a molecule, then there's presumably an exothermic reaction. Heat's given off to the surroundings, and you end up with a system that's in a lower energy state relative to the isolated atoms that you started with. And we also know that there's a bond length, or we believe that there are bond lengths associated with covalent bonds. And we also know that these atoms have these positively charged nuclei, and so therefore at short internuclear distance, where internuclear distance is r, we expect there to be a large internuclear repulsion. Right, it's going to take a lot of energy to put the H and the Cl right on top of each other, right? Because there's going to be a lot of repulsion between the primarily between the nuclei. There's some repulsion of the associated electron clouds, but at very short distances, it's really the charges on the nuclei that dominate, and you get this this large internuclear repulsion, this very steep electrostatic or Coulomb force or potential associated with that. The other thing is, in order for there to be a bond, it sort of makes sense that there's got to be some equilibrium position. So the force should be zero at R equals R0, where R0 is the bond length. And again, as we stated above, we think that maybe this potential should look roughly parabolic near the bottom. So let's take what we know here and see if we can construct a potential energy curve. So we're going to have V, and this has to do with V of HCl. So this would be the potential associated with the electrostatic and quantum mechanical interaction of the H and the Cl. And so we're going to have V along increasing here along the y-axis, and we're going to declare a 0, and we're going to have so that's V equals 0 there, and of course we're going to have an R equals 0 position there too. So that's R equals 0, V equals 0. And so now we have our coordinates. And I said previously that, let's see, we have this large internuclear repulsion, and we know that force is equal to minus dV dr, and there would be this large force to the right at very short r. So there'd be this large repulsive force, and so therefore there should be a negative slope, and it should be a steep negative slope. And so here it's gonna look like this, right? That's a negative slope. Okay, and then we expect that at some large distance, basically we end up with the energy of the dissociated molecule, energy of H plus energy of Cl. And in between, we expect there to be a place where the slope is 0. And so this would be this would be at R0. That would be at the bond distance. At the bond distance, you would expect the potential to be flat. If the potential is flat, then there's 0 force. Right? So if the potential is perfectly has a slope of 0, then there's 0 force. So that's then we can also mark up where does the bond energy show up? Well, if this energy over here is the energy of the dissociated molecule, and then this energy here is the energy when you have a molecule, then the difference between those two energies, roughly, is the bond energy. So if we want to dissociate this molecule, we need to supply energy, perform work to sort of pull these two nuclei apart, and the work required is going to be the difference in the potential at these two places, at the sort of very large R limit, where R is maybe 5 times R0 or 10 times R0. At that point, the curve's roughly flattened out, and the nuclei are far enough apart that they're not sort of seeing each other in an electrostatic sense. So you have a fairly flat curve. But if they get close enough together, of course, they'll re-react and form a molecule again. And so this is roughly what this curve looks like. Now, I mean, I haven't proven it, but it turns out that in this region, sort of within, I don't know, 0.8 R0 to 1.2 R0, something like that, that's the parabolic region. That's roughly. Now, the fact that it's not exactly a parabola doesn't mean that it's a lie. It just means that it's an approximation, and that's okay. In science, we have approximations. We don't want to necessarily take the time in every instance to calculate something to 20 significant figures. It depends on what are we trying to do. In this case, we're trying to understand what's going on and kind of put our harmonic oscillator in context of what does an actual molecule look like, just so that we don't make the mistaken assumption that covalent molecules are literally harmonic oscillators. No, that's not true. It's an approximate model. It's not a falsehood, but it's a useful abstraction. But it's good to know when you're dealing with an abstraction. It's good to know different levels of abstraction, different levels of detail for your model. Whenever you have a model, you're leaving out some things, at least temporarily. You can always add them in later, perhaps, or typically, but so it's not a really big problem. But anyway, so yeah, so this is a little bit deeper level to look at this. And we can see where a bond energy shows up. So now in a harmonic oscillator molecule model, there is no bond energy, right? It's just you have this parabola that extends up on either side. In this case, outside of this parabolic region, there's a pretty substantial deviation from parabolic behavior. But as it turns out, most molecules are in the lowest energy vibrational state, and there may be some infrared transitions taking you to the first excited vibrational level, the V equals 1 level, and so we're down near the bottom of that in that parabolic region, and the wave functions don't extend much past the sort of 0.9 R0 to 1.1 R0 type region, and so there isn't much probability density in the non-parabolic regions. And therefore, the harmonic oscillator turns out is a pretty good approximation, at least for the lower vibrational states. Now, if you stick this molecule in some kind of high-power laser where you're exciting, putting it into the V equals 10, V equals 20 level, then obviously the fit between the harmonic oscillator and your actual chemical system is not going to be as good, and you're going to need to have a better, more detailed potential model that's going to take that into account. And let's see, what else did I want to say about this? But yeah, so this harmonic oscillator is pretty good at room temperature to deal with room temperature vibrations. It's not going to give us things like bond energy and bond length. We need a higher level model to deal with that. And then you might wonder, how do we know this is true? Okay, so we sort of constructed this based on some arguments, right? That there has to be a bond energy, that at very large R, you're going to get the energy of the dissociated components that went into the molecule, and that at very short R, there's going to be this huge Coulombic repulsion. So we sort of constructed this. Then the question is, how do we know, is this actually the case? And yeah, so there's a couple of ways to tackle that. One is to solve the Schrodinger equation for the full system with all the electrons in it. And we haven't talked about how to do that yet, but there's a but we can calculate V for this kind, for say a diatomic with what's called ab initio quantum chemistry software. Such as Gaussian, games, NW-Chem, Gaussian and NW-Chem, and I think maybe some others like VASP are up on the Palmetto cluster, and you can use them to calculate these kinds of potential energy curves and solve a lot of quantum mechanical, make a lot of predictions about molecules using quantum mechanics. In the PChem lab course, we often use games. It runs nicely on a desktop, and in fact, you can download it for your own PC without paying for a license if you're just using it for educational use. And I believe NW-Chem is also freely available, but it is not set up in the PChem lab. So that's so we can use higher level theory to get one of these curves. That's somewhat satisfying. We can also measure forces between atoms using an atomic force microscope. And you get a curve that looks very similar to this. So yeah, so that's our best understanding, is that these kinds of curves look roughly like this, and that it's often a pretty good approximation to approximate the vibrations of a molecule using this harmonic oscillator. But if you want to know about things like bond energy, bond distance, or if you want to know what's happening up closer to this dissociative region, then you're going to have to use higher level calculations. And that is it for this lecture. Our next topic will be the quantum mechanical rigid rotor.